Right, so the last two chapters on this course, 9 and 10, like I mentioned before, I'm going to sort of merge them together. And the topic is on Lewis structures, okay, building these molecules. Okay. So if you like construction, maybe you'll like this last part of the course. No, you don't like construction, Adriana? Okay. Three-dimensional shape of molecules. Okay, before we go there, I want to give you some ground rules. Okay, so ground rules for Lewis structures. Okay, the first rule is that carbon loves 4. Oh, what happened? I'm so aloof, so out of there. All right, ground rules for Lewis structures. Thank you for telling me that. Okay. The first rule is that carbon loves 4. Okay. Carbon loves or is at happy at 4. Carbon is happy at 4. That means it has 4 valence electrons. All right, so here's how we're going to depict this. Carbon, 1, 2, 3, 4. Okay, you see that little dot there? Okay, that's ready to make a bond. Okay, that's ready to make a bond. This one here on the left, make a bond. Same thing with the right, and then same thing at the bottom. Okay, it will make a bond to an atom. Okay, any atom or a collection of atoms. Yeah, I'm just going to call that R. Okay, it doesn't matter. Don't worry about R. Okay, it's just our focus is on the carbon. Focus is on the carbon. Okay, if you go into more higher level chemistries, they'll call this outer atom the substituent. Okay, which is just the outer atom. But we are concerning ourselves with carbon and how it's happy at 4. So what I want you guys to do is just count with me. Okay, carbon loves 4. Okay, it absolutely loves 4. Okay, loves 4. So 1, 2, 3, 4. So let's do an example here. Okay, let's replace the R's with hydrogen, and we'll get CH4, which is methane. CH4, which is methane. So just replacing the R's with hydrogens. Okay. Single bonds, these are all covalent molecules. So carbon loves 4. Okay, here's another example where we have it with a double bond. Okay, so biology majors, I think you're a biology major, Adrienne. And Josh is a theater major, right? Okay, he can appreciate this. I don't know about the theater major and Josh, but this molecule is called formaldehyde. It does a lot of things, makes you blind. Yeah. Also, Harper is a chemistry major. I should give shout out to him. He's one of us.
No, we had a chemistry major.
That's right here.
The only one.
The only one. We want more.
You want more.
Formaldehyde. Okay, CH2O. Here's an example. Remember, carbon loves 4. Okay, it must have 4 no matter what. So this is how you're going to get 4 to that carbon. Okay, forget about the other atoms. Okay, only focus on the carbon. Okay, so you're going to count with me. 1, 2, 3, very good, 4. Okay. So it has to have 4. Okay, let me give you another example. This is called cyanic acid. HCN. Okay, so it's going to be H, single bond C, triple bond N. Again, don't worry about the H and the N. I just want your attention focused now with me on the carbon. Carbon happy at 4. 1, 2, 3, 4. Okay. Carbon is very happy in these types of states, whether it's a single bond, double bond, or a triple bond. Okay. So carbon loves 4. If you take organic chemistry, it's all about carbon and 4, the number 4. Okay, next one on our list in rules is nitrogen. Nitrogen is happy at 5. Okay, so here's how we'll do nitrogen. 1, 2, 3, 4, and then 5. Okay, so here we have what's called a lone pair. Nitrogen has a lone pair. So you guys see that little dot here? I'm going to have that ready to form a bond, okay, with something called R. Don't worry about R. It's just any R group substituent. Same thing with the right, and then same thing at the bottom. So let me give you an example of this. Okay, we'll replace the R's with H's and get NH3 ammonia. Okay, NH3 ammonia. So here is ammonia. All right, I want you guys to count with me. All right, 1, 2, 3, 4, 5. That is a content nitrogen at 5. Let's hop back up to cyanic acid. Okay, so just count with me here, focusing on this nitrogen. Ready? 1, 2, 3, 4, 5. So this is an example of nitrogen that's sort of in a good state. Right, the next one on our list is oxygen. Oxygen is happy at 6. Okay, oxygen is happy at 6. Right, so I'm going to have the 6 valence of electrons. 1, 2, 3, 4, 5, and 6. Okay, here we have not 1 but 2 lone pairs. So you see that dot? Okay, I'll have it form a bond with something called R. Okay, don't worry about R. It could be anything. But this is one way, and we can get oxygen to be at. All right. I'll replace the R's with simple hydrogens, and we'll get the beautiful molecule of water. Okay, so H, single bond H, H. Okay. So once again, let's count. All right. Ready? 1, 2, 3, 4, 5, and 6. That's shared. So 1, 2 shared. 3, 4, 5, 6. Right, let's hop on over to formaldehyde. Okay. Let's see if oxygen is happy here. Ready? 1, 2, 3, 4, 5, and 6. Okay, so these represent very good Lewis structures. All right, next one is the halogens: fluorine, chlorine, bromine, iodine. These are called the halogens. Okay, these are happy at 7. 7. Happy at 7. Okay. So I'm going to pick on chlorine here. 7. So 1, 2, 3, 4, 5, 6, 7. Here we got here we got 3 lone pairs. And And this can be fluorine, this could be iodine, it could be any one of those. So I'm going to have, you see this dot, okay, I'm going to have it form a bond with anything. Okay, we'll call that anything R. And that would be one of the halogens. Let's give an example. Let's replace the R with a hydrogen. And we have hydrochloric acid. One thing I want to tell you guys is that chlorine is going to pull. Okay, the chlorine is going to pull because chlorine and bromine and iodine and fluorine, these are what we call electronegative atoms. So it's not a 50-50 bond, it's really a pull. That's really pulling the chlorine and the bromine. You know, I'll do hydrobromic acid. It's not an equal bond. Okay, so some examples of covalent molecules. Okay, get ready to count with me. 1, 2, 3, 4, 5, 6, 7. Okay, so halogens are going to be happy at 7. Almost finished with our ground rules. Right, let's do rule number 5, and that's hydrogen. Hydrogen is happy at 1. So there's that one valence electron of hydrogen, and yeah, it's just going to form a bond, okay, with some substituent R. Okay. And again, we're not worrying about R, we're just worrying about the hydrogen. As an example, let's talk about H2 gas that's present in our atmosphere. Okay, so replacing the R with H, and you have H2 gas. So let's look at this hydrogen here. 1. It's good. Let's look at this hydrogen here in HBr. 1. Let's look at this hydrogen here in water. 1. This hydrogen here in water. 1. This hydrogen here in ammonia. 1. Okay, so 1. Hydrogen is happy at 1. Right, rule number 6 is that aluminum and boron are happy at 3. Okay, so aluminum, I can also do boron. 1, 2, 3. 1, 2, 3. So instead of that little dot there, I'll just have it ready to form a bond, okay, with R. Again, don't worry what R is. It could be one atom. It could be a collection of 10 atoms. We're not worried about it. We're just worried about boron and aluminum. Happy at 3. So as an example, let's replace all the R's with hydrogen. So aluminum trihydride. So okay, that's one Lewis structure. I can replace the R's with chlorine. I'll get boron trichloride. Another example. All right, so count with me here on the aluminum. 1, 2, 3. Count with me on the boron. 1, 2, 3. So I'll stop there with the ground rules. Okay, we can go on. I'll stop there for now. So what's the point of all of this? Okay, goals. Okay, the goals in Lewis structure is to, number 1, minimize formal charge. Okay, FC. Okay, formal charge is happy. The formula for this is happy minus number of electrons around atom. Number of electrons around atom. So that's goal number 1. You want to minimize formal charge, FC. And then goal number 2, this goal is not as important, but this is important. Okay, goal number 2 is to try to get an octet. Okay, but let me tell you right now, there's a lot of exceptions to this octet rule. Okay, there's a ton of exceptions. Okay, so you're going to see exceptions. One of the exceptions is expanded octet. Okay, so lots of exceptions. Okay, number 1, we have something called expanded octet. Number 2, we have incomplete octet. So hydrogen, the octet rule is actually 2. Okay, hydrogen, there's no way hydrogen. It's a very puny element, you see. So its octet is actually 2. And then aluminum and boron, its octet rule is actually 6. So that is the goal here. We want to get our formal charge minimized, and the octet rule is important, but you're going to see expanded octet. You'll see that in the examples. You'll see that in the homework. I know I filmed some videos where there's expanded octet. So this is what we're going to be focusing in on now from here till the end of the class. All right, so let me go over this formal charge and octet rule considerations. All right, so let's go back to our examples. Go back to our earlier notes here. Okay, carbon and methane. Okay, so the first thing we want to do is the formal charge. All right, formal charge, focusing on this carbon. All right, so ready? 1, 2, 3, 4. What is carbon happy at? 4. What's 4 minus 4? 0. Okay, so that is formal charge. Okay, the octet rule. Here, the octet rule, you count everything individually. Here in the octet rule, you count everything individually. So it's shared 1, 2, 3, 4, 5, 6, 7, 8. So the octet rule for this carbon is satisfied, realizing that you can have a lot of exceptions, particularly expanded octets. All right, let's look at this hydrogen here. Okay, realizing this hydrogen, and this hydrogen, and that hydrogen are all the same because they're all bound to carbon. So look at this hydrogen here. 1. 1. What is hydrogen happy at? 1. What's 1 minus 1? 0. So the formal charge on that hydrogen is 0. All right, what about the octet rule? Here you count everything individually. 1, 2. Remember, the octet rule for hydrogen is a little bit different than all the rest. Let's look at formaldehyde. All right, formal charge of the carbon. Ready? 1, 2, 3, 4. What is carbon happy at? 4. What's 4 minus 4? 0. Okay, the octet rule for this carbon. Ready? Count everything individually. 1, 2, 3, 4, 5, 6, 7, 8. So the octet rule is satisfied. What about this what about this oxygen here? Okay, formal charge. Ready? Formal charge, not octet rule. 1, 2, 3, 4, 5, and 6. What is oxygen happy at? Oxygen is happy at 6. Good. 6 minus 6 is 0. Okay, the octet rule for this oxygen. Ready? Count everything individually. So this is shared in the double bond. So 1, 2, 3, 4, 5, 6, 7, 8. Let's look at this nitrogen here and cyanic acid. All right, ready? Formal charge. Nitrogen. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. What is nitrogen happy at? 5. What's 5 minus 5? 0. Octet rule for this nitrogen. Okay, 1, 2. Count everything individually. 1, 2, 3, 4, 5, 6, 7, 8. Carbon. Okay, ready? 1, 2, 3, 4. Calculating formal charge now. 1, 2, 3, 4. Carbon happy at 4. 4 minus 4 is 0. Okay, let's look at the octet rule here. Count everything individually for this carbon. 1, 2, 3, 4, 5, 6, 7, 8. So these are all the best structures. This is the best structure of formaldehyde. This is the best structure of cyanic acid. Okay, let's do this hydrogen here. Okay, 1. Hydrogen happy at 1. 1 minus 1 is 0. Octet. 1, 2. The octet rule for hydrogen is 2. So this is how you draw your Lewis structures. It's like a little bit of a game. Okay. Let's do one more, and then we'll just hit you with a bunch of different examples. Okay, for practice. All right, oxygen here. Formal charge. Okay, formal charge now. 1, 2, 3, 4, 5, and 6. Oxygen happy at what? 6. Very good. 6 minus 6 is 0. Octet rule for this oxygen. Count everything now. 1, 2, 3, 4, 5, 6, 7, 8. And we already talked about this hydrogen, but I'm just going to sort of ram it down you. Okay, 1. Hydrogen happy at 1. 1 minus 1 is 0. Octet rule. 1, 2. That's the octet for hydrogen. Remember, there's a lot of fuzziness with the octet rule. All right, so our little bit of the basics are down. So now let's just draw some of these. All right. remember in your flashcards, you had something called a hydroxide ion. Okay, it was a flashcard thing that you memorized in the first week. So let's draw this. All right, oxygen is happy at 6, right? Oxygen is happy at 6. Hydrogen is happy at 1. What does that minus sign mean? Add an electron or lose an electron? Okay, the minus sign means you add an electron, right? Is that correct? You agree? So I have to get 8 valence electrons around the hydroxide ion. Okay, 8 valence electrons. So here we go. I have my oxygen bound to my hydrogen. 1, 2. Where will 3, 4, 5, 6, 7, and 8 go? Will it go on the hydrogen? Okay, no. 1, 2, 3, 4, 5, 6, 7, 8. I got my 8 electrons. Now let's do our formal charge and octet rule. Okay, let's do our formal charge and octet rule considerations. Let's first do hydrogen here. 1. Hydrogen happy at 1. 1 minus 1 is 0. Octet rule for this hydrogen. 1, 2. The octet rule is satisfied. All right, oxygen, formal charge. Okay, ready? Everyone watch this. 1, 2, 3, 4, 5, 6, 7. What is oxygen happy at? 6. What's 6 minus 7? Okay, so that oxygen has that minus formal charge, which is what you saw in the problem, you see. That's what you saw in the first place when you the problem. So the minus sign in hydroxide ion, that flashcard that you did many, many weeks ago, that minus sign is on the oxygen. All right, octet rule for this oxygen. 1, 2, 3, 4, 5, 6, 7, 8. You count everything individually for the octet rule, and that is the correct formal structure for the hydroxide ion. Okay. That is the correct formal structure for the hydroxide ion. How about CO2, carbon dioxide? What is carbon happy at? 4. What is oxygen happy at? 6. But how many oxygens do we have? 2, right, Adrienne? We have 2 oxygens. So our goal is to get 15 valence electrons around the CO2 molecule, carbon dioxide. What do you think our center atom will be? Carbon. Okay, we have 2 oxygens. I don't know which oxygen is center. Okay, I don't know. So, carbon. Carbon. Okay, now what? Carbon loves 4. Okay, like life or death, carbon has to have 4. So how will it get 4? Yeah, okay. 1, 2, 3, 4. All right, ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And that's how I get my 16 valence electrons around CO2. All right, let's do formal charge and octet rule for this carbon. Okay, formal charge, 1, 2, 3, 4. What's carbon happy at? 1, 2, 3, 4. Carbon happy at 4. What's 4 minus 4? 0. All right, the octet rule for this carbon, 1, 2, 3, 4, 5, 6, 7, 8. So you count everything as a dot. Count everything as 1 for the octet rule because it's shared. All right, formal charge for this oxygen here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oxygen happy at 6. 6 minus 6 is 0. Octet rule. Count everything as individually in the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. So that is the octet rule for carbon dioxide. For the oxygen and carbon dioxide is satisfied. All right, another thing I want to tell you, you see this C double bond O? Okay, I want to tell you it's not a 50-50 sharing. Even though it's a double bond, it's not equally shared. You see this oxygen is oxygen is one of those electronegative elements. You see this oxygen is going to pull this way. It's pulling. And it's going to be partial negative because oxygen is a partial negative. Oxygen is an electronegative atom, excuse me. I'm searching for something that I seemingly cannot find, but and what about this oxygen here? Is it the same thing? It's the same thing. So this oxygen is pulling this way. That oxygen is pulling the opposite way. They cancel each other out. This is a non-polar molecule. Non-polar molecule. Okay, finally I want to tell you is that CO2 is, look at this center atom, is a carbon. Okay, how many bonds are attached to the carbon? Okay, we have 2 bonds. They happen to be a double bond. We have 2 bonds. Okay, 0 lone pairs. 2 bonds and 0 lone pairs. If you look at table 10.1 in your textbook, okay, make sure you bring 10.1 and 10.2 to the exam, your home exam. You'll realize 2 bonds and 0 lone pairs is a linear geometry. So this molecule is actually linear. Linear molecule. Okay, linear. It's a straight line. 2 bonds, 0 lone pairs on the carbon. Okay, 2 bonds, 0 lone pairs. So okay, so how will we get to 2 bonds and 0 lone pairs? Now I'm going to introduce to you something called hybridization. Okay, which means mixing of orbitals. So how will we get to 2 bonds and 0 lone pairs? Okay, well, S has 1 slot, P has 3 slots. Okay, so to get to 2 bonds, we're going to take 1 of S, that's 1, and then where will we get the second one for 2? Okay, we'll get it from P. So this is called an sp hybridized carbon. sp hybridized carbon. Okay, so 1s, don't put s1p1, just put s and p. So 1s plus 1p is equal to 2, and that's your 2 and 0. So carbon dioxide is nonpolar, and it's an sp hybridized carbon. We took one s and one of p. 1 plus 1 is 2. That's your 2 bonds and 0 lone pairs. Okay, so on your test, make sure you have table 10.1 and table 10.2. Okay, I got table 10.2 here. The difference between 10.1 and 10.2 is that this is dealing with lone pairs. Okay, table 10.1 is 0 lone pairs, such as this example. Let's do a couple of more here. Ammonium ion. NH4 plus. All right, so nitrogen is happy at 5, right? Hydrogen is happy at 1, but we have 4 of them. And then what do you think that plus means? Did it give up an electron or gain an electron? It gave up an electron, so -1. So our goal here is to get 8 valence electrons around the ammonium ion. Okay? Ammonium ion. So, what's our central atom? Not hydrogen. There's which of the 4 hydrogens? No, it's not hydrogen. It's nitrogen. Okay, so nitrogen. 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6, 7, 8. So there is my 8 valence electrons. Okay. Let's do formal charge on this nitrogen here. Formal charge. Nitrogen. 1, 2, 3, 4. What is nitrogen happy at? 5. What's 5 minus 4? +1. So this nitrogen has a positive formal charge. Well, you knew that because that's what they tell you in the problem, okay? You knew that because the problem tells you it's positive charge. It's just so that the positive charge is on the nitrogen. Okay? Octet rule. So this was formal charge. The octet rule for this nitrogen: 1, 2, 3, 4, 5, 6, 7, 8. Hydrogen here. All right, hydrogen 1. Hydrogen happy at 1. 1 minus 1 is 0. Octet rule for the hydrogen: 1, 2. That's the octet rule for hydrogen. All right, looking at the center of nitrogen, how many bonds and how many lone pairs? 1, 2, 3, 4. Okay, 4 bonds. 0 lone pairs. Okay, do you see any lone pairs on the nitrogen? 4 bonds, 0 lone pairs. 4 bonds, 0 lone pairs. Okay, look at table 10.1 in your book, okay, which I don't have, unfortunately. So, table 10.1 in your textbook, and again, you can bring 10.1 and 10.2 to your exam. Okay, you'll see that the molecular geometry of this is tetrahedral. Okay, tetrahedral. So this molecule is the shape of a tetrahedron. Same thing with methane. Okay, same thing with methane. Okay, tetrahedral. Okay, so how do you draw a tetrahedron? Okay, so have your nitrogen. I'll have one of the hydrogens go be on the plane. The other hydrogens be here. Okay. I'll have one of the hydrogens sort of come out away toward towards you. Okay, this means it's coming towards you guys. And then I'll have the other nitrogens going away from you guys. And don't forget this has a positive formal charge. So that's how you would draw it in 3 dimensions. This type of bond is called a wedge. The one that I colored purple or orange. And this one with the lines is called dash. Okay, try to get something 3 dimensions on a 1-dimensional piece of paper. Now let me tell you what's cool about this. So tetrahedral, 4 bonds, 0 lone pairs. Very beautiful, perfect bond angles of 109.5 degrees C. But let's see, this is very interesting, at least to me. So if you take the center of each atom, center, 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 and draw a line connecting the centers, and your professor's not a Picasso here, but you get something that's like a tetrahedral. Okay. Say that again? I'm sorry, I didn't hear you.
No, I said, look at that.
Oh, look at that. Yeah, see? So 4 bonds, 0 lone pairs, tetrahedral. All right, how will we get to 4? Okay, we're going to take 1 from S. 1 from S, and that's 1, and then 3 from P. So this is an sp3 hybridized nitrogen, right? 1s plus 3p is 4. So yeah, sp3 hybridized nitrogen. Okay. Same thing, this would be an sp3 hybridized carbon. Okay, 4 bonds, 0 lone pairs. Let's do water. Okay, so I think next week we'll have more examples and a couple of other things I also want to talk about, and then we will, we'll say bye-bye to each other. I think I'll see you two later in 2021. Okay, oxygen, and you also. I think you registered. Okay, that's great. I'm happy for that.
We'll be saying bye to
Yeah. Oxygen is happy at 6. Hydrogen is happy at 1. But we have 2 of these, right? So our goal is to get 8 valence electrons around the H2O molecule. Oxygen is going to be our center atom. Okay. Right, oxygen happy at 6. Hydrogen happy at 1, but we got 2 of those guys. Chem 2 is a lot harder than Chem 1. It's just, I don't, but. So we got to get 8 valence electrons. So oxygen with a hydrogen and a hydrogen. 1, 2, 3, 4, 5, 6, 7, 8. Okay. All right, again, I will be beating a dead horse. 1, 2, 3, 4, 5, 6. Oxygen happy at 6. 6 minus 6 is 0. Octet rule, 1, 2, 3, 4, 5, 6, 7, 8. Octet rule is fine. Okay. All right, looking at the center oxygen, how many bonds and how many lone pairs? 2 bonds. How many lone pairs? How many bonds, how many lone pairs? Lone pair 1, lone pair 2. 2 bonds, 2 lone pairs. You see that? 2 bonds, 2 lone pairs. So what's the geometry? 2 bonds and 2 lone pairs. Okay, this is when on your exam you're going to consult this. Okay, why consulting 10-2 instead of 10-1, Harper? Because 10-2 is with what? Lone pairs. And here we've got 2 lone pairs. Okay, so 2 bonds, 2 lone pairs. Okay, you're going to look at geometry. Okay, you're not going to look at this. This is a little different. You're going to look at the shape of the molecule. The shape of the molecule is bent. Bent. Okay, look at all these different 3D shapes. But for water, it's bent. Look, they even gave you the example of water. Bent. Okay, bent. So how will you draw something bent in 3 dimensions? Okay, it's going to be like this. Bent. Okay. So the geometry is bent. This makes water, for the biology majors, this makes water, this bent thing is not trivial, this geometry. It gives it a lot of amazing features and properties which many scientists believe is instrumental for life, to life. Okay, you see, many people think water is linear. Okay, I taught a biochem class, and I asked them, what's the structure of water? And they said, oh, it's linear. Okay, no way, nothing can be further from the truth. And people believe if water was a linear molecule, straight line, 180 degrees, if water was linear, like CO2, we wouldn't have life on this planet. Okay, but it's bent. Okay, so those 2 lone pairs really, they distort the molecules such that you get a very unique bond angle. I don't know the bond angle off the top of my head, but of all the millions of molecules on Earth, okay, water is the only one that is, to my knowledge, has that bond angle, 107, 108, whatever. You can look at Google. But no other molecule seems to have that unique bond feature, bond angle between this H, that H, and that H. Okay, so the geometry is bent. The 2 lone pairs bend the molecule. It's not linear. 2 bonds, 2 lone pairs. Okay, so how will we get to, what's 2 plus 2? 4. So how will we get to 4? Okay, we're going to take 1 from S. And how many from P? 3. Okay, 3 plus 1 is 4. That allows for my 4 bonds. Okay, 4 bonds, 2 of which are single, 2 of which are lone pairs. So one of the lone pairs, I guess both lone pairs are going to go to the P, and then the bonds are going to go to S and then one of the P's. The way you do hybridization is that 1S plus 3 is 4, 2 plus 2 is 4. Okay, so this is an sp3 hybridized oxygen. This is an sp3 hybridized oxygen. Just like, go back to our previous slide, this is an sp3 hybridized N, nitrogen. This is an sp3 hybridized carbon. Okay, but this is 4 bonds, 0 lone pairs, so table 10.1. 2 bonds, 2 lone pairs, table 10.2, or whatever internet table you use. Okay, and you'll see the geometry is bent. Okay, so sp3 hybridized carbon, shape is bent. Finally, this is a polar molecule. Another reason why many people think water is such a fascinating molecule, not only because of its unique bond angle, but the polarity gives it some unique capabilities, one of which is called hydrogen bonding. Okay, so water is polar. Okay. Final thing here, these guys are not polar, right? NH3, sorry. Okay, this is not polar. Okay, hydrogens have no pulling power, so that's not polar. Okay, the pulling power comes from the oxygen. Okay. All right, it's 9:50, and I guess we will have class Monday. On Monday, we will go through more examples. For those that want to get ahead, look up resonance. Okay, that's the next thing on our agenda, and that's what I'll be lecturing on Monday. I will also have a lecture Friday, just like this. Wednesday, do you guys know? my understanding it's a holiday for Veterans Day. Is that true? Okay.
Yeah.
Yeah.
It's on the calendar, so.
Yeah, if it's on the academic calendar. So I'll see you guys next Monday. I'll see you guys next Friday. And thank you for coming. And I appreciate all of you for coming, all three of you. Bye-bye, Harper.
Have a good rest of your day.
You too. Bye, Josh. Bye, Adrienne.